All right, so let's talk about where log scales are used in the real world. So we know what a logarithm is. And one of the things I showed you yesterday is one of the applications of logarithms, and it has to do with when you're solving for an exponent in a finance related exercise. So finance, compound interest at any rate, is an exponential sort of scenario. And the fact is that if you have to solve for the exponent, then logs is really the way to go in that kind of situation. But let's talk about where logs are used elsewhere. And for this, I'm going to be drawing on things that you probably have learned in other courses, physics and chemistry and so on. So a lot of you will be familiar with the pH scale. What we're looking at right now is the pH scale, and the formula for the pH scale, in case you haven't learned this before, is that pH is equal to minus the log of what are called, or what is called, the hydronium ion concentration. What does that mean? Well, if you look at a substance like an acid or an alkaline, the amount of hydrogen ions that you have in a particular volume, right, will determine whether that thing is acidic or alkaline or is alkaline. So if the scale generally goes from, I mean, I should be asking you this, you probably know this already, from 1 to 14. And things that are acidic tend to be on the lower end of the scale. Things that are alkaline tend to be on the higher end of the scale. So what we do is we take the log of the hydronium ion concentration, and because that number is generally very small, it tends to be a negative number. Let me just sort of make sure people understand this. The log, and I'm just going to just demonstrate this to you right now. Hydronium ion concentration is in terms of moles per liter. And that tends to be pretty small. So a number like, for instance, 0.002, let's just use that as an example. That number is going to be a negative number, right? Why is it negative? Because 0.02 is actually 1 over, actually 2 over, what is that? 1, 2, 3, 2 over 1,000. That's what 0.002 is. So that means that you're looking at a number. If I'm saying, what number do I raise 10 to get this decimal number? That's going to be a negative number, right? So numbers that are this small are going to be negative. So in order to make it positive, they put a negative sign in front of the log of this hydronium ion concentration, and that turns it from a negative number to a positive number. So it's really that simple. Okay, now why do we use log scales? And I think it's important for me to sort of talk about that a little bit. Log scales are used in the real world when the thing that you're measuring tends to vary greatly. So, for instance, the one of the things that we measure on log scales is sound, right? Decibels. We're going to get into that in a minute. And the fact is that very low levels of sound compared to very high levels of sound have a huge difference in terms of their intensity. So in order for us to wrap our brains around that, what scientists did is they put them on a log scale, which sort of narrows down how wide that scale is. So whereas the difference between a very low sound, a very quiet sound, and a very high sound is vast, putting it on a log scale makes it more manageable for us. And that's the reason, and that might come up as a question in a multiple choice or something like that. That is the reason that we use log scales to kind of narrow down the range of something that we're measuring. So it does apply to the acidity or alkalinity of a substance, right? It's a very wide scale. So we use the log scale to narrow that down. So here's a very simple formula for it, right? It's the negative of the log of the hydronium ion concentration. And hydronium ion concentration is measured in moles per liter. Okay, so it's very simple. If tomato juice has a hydronium ion concentration of approximately, and I give it to you here as 0.0001 moles per liter, what is its pH? Well, that's, hold on, I've not been monitoring the chat here. Sorry, let me go back there a little bit to make sure I'm not missing anything. No, I'm not. So it's pretty simple. What we're going to do is we're going to say that the pH is equal to minus the log of 0.000, is that 3 zeros? Yeah, 1. Okay, Now, for me, this is not a difficult thing for us to work out because what we can do is we can express this. I mean, you can use a calculator, clearly. And if you did your calculator right now, you would get a number on your calculator. In fact, you can go ahead and use your calculator. Go ahead and use your calculator and find the log of 0.001. And it works out to be, of course, -4. So what you're getting is minus 4, which of course is just simply equal to 4. So it's really that simple, right? It's really that simple. I could have done this in my head because I know that if I move the decimal point here, 1, 2, 3, 4, that's going to take me to 0. So if I move it back, it takes me to -4. So of course the log of 1 is 0, which we talked about before. Every time I move it to the left one decimal place, it goes down by one number on the log scale. So -1, -2, -3, -4. So there you go. So there you go, folks. That's the first calculation, very simple calculation. All we have to do is just simply put it into the function, into the formula rather, and you have an answer. Okay. On the other hand, what if you wanted to find the concentration of hydronium ions in orange juice? Well, they're telling you that it has a pH of 3. It's acidic. I mean, that's what I said before. Anything from 1 to I think it's 7, 7 is neutral, is considered to be acidic. So we're going to just simply put 3 equal to, because remember the function says that pH is equal to this. So we're going to take 3 and set it equal to minus the log of the H plus. Right? We're trying to solve for the H plus. Okay. So how do I do that exactly? Right? How do I solve for the H plus? I'm going to go with what Roma suggested first, which is to divide through both sides by -1. So let's start with that. Okay, so this side becomes -3 is equal to the log of the H plus. Okay, but how do I now isolate, put it in, thank you, Brenda, right? Put in exponential form. I kind of understand what Mohammed is saying, but let's just sort of make sure we shift our focus away from trigonometry for now. I know what you're saying is find the opposite of sine, like sine to the -1. It's kind of similar, except the inverse of this is an exponential function, or log function rather, is an exponential function. So Brendan is right. Well, what does this look like in exponential form then? Right? Not just Brendan, but what does H plus equal the hydronium ion concentration if it's an exponential form? Brendan is right. 10 to the -3, correct. So I don't need a calculator for that. So that's going to be 0.001, and that's in moles per liter, right? I don't need a calculator because, like I said to you, if I move the decimal point from here, every time I start at, so starting at 1, if you can see where I'm pointing to now, if I start here, right, if my decimal point was here, then I'd be at 0. This would be -1, -2, and -3. So this should be the hydronium ion concentration with the correct units as well, moles per liter. And that's all it is. That's all there is to understanding the pH scale as a log scale. That's really all it is. Okay? So far so good. Decibels, like I said, is a log scale because of the wide range in sound intensities. Now, the truth is that sound intensities are measured in sort of real terms in something called watts per meter squared, right? It's the amount of power, which is what you measure watts by, in a certain amount of area. So it's watts per meter squared. But like I said, because of the wide scale of sound intensities measured on that scale, the log scale is used to narrow that down. Having said that, right, one of the things that I want you to bear in mind is that they have come up with what's called threshold of human hearing, and you see I have it on the screen here as being 10 to the -12 watts per meter squared. So what's happening is that there is sound intensity below that, but we as humans can't hear it. It's just too low for our biology, the way we're made up, doesn't allow us to detect sound that is below that intensity. And that comes up on the decibel scale as 0. So we're going to use that as 0. Not that you can't have a lower intensity, but for our purposes, we just rate that as 0 because we can't hear anything lower than that. Okay, so what is this decibel scale? Well, I have a thing here which came from the textbook which shows you different numbers that are associated with certain decibel levels. So it's very quiet at about 10 decibels, rustle of leaves, a whisper, that kind of thing. And as you go up, it gets up to levels of 200 and beyond. And as you see, it says on the screen, potentially fatal. You could burst your eardrums. There's also the pain threshold here. This could actually be very painful. You're at a rock concert, there's a jet engine. This kind of sound intensity is not the kind of sound intensity you want to expose yourself to because it's potentially harmful, right? People actually could burst their eardrums with sound intensities that are way beyond this. Not just painful, but literally lethal. So that's why this scale exists for us to be able to measure these different intensities. So where we mostly are is in and around the 60 to 80 here. 60 is normal conversation. And if you ever download, can you scroll up a bit, please? Okay. If you ever download one of those apps, and maybe I will show it to you after the break. I'll show the app that's on my phone that I use to measure sound levels in a room. But there are tons of them. It's not like this is the only one. There are tons of them that are available that you can put on your phone or a tablet that will measure sound intensity. Okay, Mohammed, you see what you wanted to find? Okay, you're welcome. All right, so like I said, this is just an idea of the different decibel numbers that you can associate with different things. All right, so barely audible at 30, that's a whisper, up to rocket, which is potentially fatal. All right, now you saw the formula. You saw B2 minus B1 is equal to 10 times the log of I2 minus I1. What does this all mean? The B's refer to the decibel levels. So if you have two decibel levels, right, you can compare them by subtraction, and that will be equal to 10 times the intensity. So the I2 and the I1, that refers to this watts per meter thing that we're talking about here, right? If you have the sound intensities measured in watts per meter, you can take the ratio of those things, right? And look at the top value. The top value is the louder, more intense sound. That's your I2. And that corresponds to the first number here, which is the B2. So this intensity refers to this decibel level, right? Hopefully you can see me pointing to it on your screen. So I2, that intensity level relates to B2. So for 10 to the minus 12 watts per meter squared, where that's 0, that would correspond to a decibel level of 0, just FYI. All right. All right, stepping away for a bit, but you'll be right back. Hunan says, okay, that's fine. All right. So let's see if we can come up with how many more times, as it says in question 1, as intense a whisper is to the sound of a normal conversation. Okay, so what we're doing is we're comparing intensities. Is it 5 times as intense? Is it 10 times as intense? What does that comparison look like when we compare the actual sound intensities? Not just comparing decibel levels. Decibel levels are just raw numbers. But if you look at the comparison between two, right? When you're trying to say whether one is 10 times more, 100 times more, 50 times more, how does that compare when you put it head to head like that? So that's what the question is. How many times is intense the whisper the sound of a normal conversation? Well, let's go back to the chart, look at their decibel levels. So what it says here is that a normal conversation is 30, is 60, and a whisper is 30. So when you look at that, does it suggest that one is twice as high? Well, it's not, just so you know. If you're just comparing decibel levels that way, you're missing what a log scale is. It's not that 60 compared to 30 is twice as high. So I'm going to show you right now how much more it is in real terms when you're looking at a scale which says that one is 60 and one is 30. So here we go. So what I'm going to do is go back to the formula here for a second. I'm going to take my B2 and my B1. I'm going to take the B2 as being the loudest sound, right? And say 60 minus 30 is equal to 10 times the log of. So what we're doing is we're saying the I2 is on top over the I1 on the bottom. So what That's supposed to be an I there. So what we're doing here is we're trying to find what the I2 over I1 is. What is that comparison? What is that ratio going to be? Is that number going to be 10? Because if it's 10, it means that the number on top is 10 times the number on the bottom, so it's 10 times more intense. So again, the louder sound is on top, right? That's your I2. The softer sound is on the bottom. That's your I1. That means that the 60 comes first and the 30 comes second. Okay? Are we good so far? Right? All I'm doing is plugging the numbers into the formula. Okay, Donna says yes. Good. Hussein says yes. All right, good. So, Mohammed, are you with us so far? Does that make sense so far? Mohammed, where's Mohammed? Great. Okay, so let's keep going. So I'm going to take these two and subtract them. It's going to give me 30 is equal to 10 times the log of the ratio of the intensities. So that's my I2 over my I1. Oh, kind of ran out of space there. Of course, this is going to give me 3 is equal to the log of the I2 over the I1. And we're going to do the same thing we did with the previous question. We're going to solve for this I2 over I1. So the I2 over I1 is equal to 10 to the power of 3. Remember that if there is no base, we assume the base to be 10, right? This doesn't specify a base, so we must assume that it's 10. So that's my exponential form. So what we're saying is that I2 over I1 is equal to 1,000. Or, put it another way, that I2 is equal to 1,000 times I1. All I did is I just cross multiplied there. So what we're saying is, to answer the question, how many more times as intense as a whisper is the sound of a normal conversation? Normal conversation is the I2. So it means that the normal conversation is actually, in terms of its intensity, in terms of the watts per meter squared, is actually 1,000 times more, right? Now that sounds like a huge one, which it is, right? And you're thinking it was just a difference between 60 and 30. That doesn't sound like much. That sounds like it's about twice as much, but that's not considering that it's a log scale, right? And that's why the log scale collapses that 1,000 down to something that's more manageable for us as humans to understand. But in reality, a whisper compared to a normal conversation is 1,000 times more intense in terms of watts per meter squared than a whisper. Just so we understand that. All right. Okay. Are we good so far? Let's just make sure that everybody made sense of that calculation. Does that make sense? So I need to go over any of that. Ryan and Roma are checking in, and Brandon are perfect. Okay. All right. So let's keep going. Here comes the second question. Sound level than normal, and it took, I think all these questions except the last one came from the textbook. So you can always go back and review the stuff from the textbook as well. All right. Sound level than normal traffic is 85 decibels. So in terms of our chart, you see that it's right here on the chart at the 85 decibel level, right? That's where they say that normal city traffic tends to be. So obviously it's higher than a shout, higher than normal conversation, higher than a whisper, and so on and so forth. And they're now telling us that the sound level in a snowmobile is about 32 times as intense. It's 32 times more intense than the normal city traffic. It's louder, is what we're saying. Snowmobile is louder than normal city traffic. What is that decibel level, right? What does that look like as a decibel level? So here's how I'm going to do this. Look back at the formula again. Just remind you what the formula says. Formula says my B2 minus my B1 is equal to 10 times the log of I2 over I1. That's what it says, right? So why don't I put the snowmobile as my B2, right? Then I'm going to subtract my B1, which is a softer sound. That's my 85 decibels. Remember, the B2 and the B1, those are decibel levels, right? So I know the decibel level of the softer sound. That's my B1. I don't know the more intense sound. That's my B2. So I'm going to put that as being B2 minus 85 is equal to 10 times the log. No, it says it's 32 times more intense. So what are we? We're solving for B2. Yes, Ryan, we're trying to solve for the B2. It's 32 times more intense. So what do I put as my fraction then? Well, let's put it as 32 over 1. If something is 32 times as intense, then whatever number I put on top is going to be 32 times more than the number on the bottom. So I could have put this as, here's another way I could have put this. I could have put this as 64 over 2. Again, whatever is on the bottom, right? The number on top is 32 times more. Either way, it's going to work out to just simply 32 compared to 1. The ratio of those two things works out to 32 to 1. Right? So we can just simply work this out as 32 over 1, or just simply 32, because let's face it, 32 over 1 is just 32. Right? If it's 32 times as intense, the number on top is going to be 32 times larger than the number on the bottom. It's really that simple. So I'm just going to use 32 over 1. I'm not going to use this 64 over 2 because that really is the same thing as 32 over 1. So as long as the number on top is 32 times the number on the bottom, I'm good to go. Okay, let's keep this going. So yes, and it's where did you get the 85 again from? Okay, so it's yeah, okay, so let me go. Thank you, Lynette, for answering that question. Go back up and read the question. It says the sound level of the normal city traffic is 85. So they gave us that decibel level, and I looked at the charts and I noticed that in fact a normal city traffic is 85. It says it right there. Well, sorry, it says it right there. It's 85. Okay, that's okay. So let's go back now and finish the question. Let's solve, as Ryan was asking, let's solve for the B2, right? So let's just do the math. So B2 is going to be equal to this 10 log of basically 32, right? I don't have to put 32 over 1 plus the 85, right? That is going to give us my decibel level. So that's just a simple calculator exercise at this point. So let me see if I can get somebody in the room to help me out. Let me get Shearbun. Shearbun, get your calculator for me, please. Can I ask you to complete the exercise? Hopefully you've been following along with us. Can you calculate what that B2 is, please, on your calculator? Not the kind of thing I expect you to do in your head. Nobody can do that in their head. Well, I can't anyway. So 10 log 32 plus 85. That should give us our answer. And it should be a higher number, right? So it's supposed to be louder, so it should be a bigger number than 85. Let's find out from Shearbun in a second. Hopefully everybody is working it out for themselves so that we can compare answers. And I've always liked that about this class. So if somebody gets something wrong, then most people are able to correct that person. If somebody gets something right, usually you just simply, say, yeah, you're good to go. So 100, let's say 100.1. All right, let's say 100.1. All right, so let's just look back and see where that puts it on the scale. So maximum stereo output, it looks like that 100.1 would put you in sort of that range of sound. Okay, and of course I should put units on that. And what unit makes sense in this case? What unit would make sense? What are we talking about? Of course, decibels. All right. Now, last question. What's the decibel rating of a teacher's voice? Not me. All right, no, this is not me. If that intensity is 9 times 10 to the minus 9 watts per meter squared. Okay, so what would you rate that teacher's voice at? Right, where on the scale would that be? Well, we didn't get any other decibel level to compare it to, but here is something that we do know. Let me take you back to the top of the page. And if I gave you a question on a test that was like this, I would still give you this information. You would have to memorize this. I know the threshold of human hearing is 10 to the minus 12 watts per meter squared. So this is rated as 0 on the decibel scale. That's enough for us to set this up, right? If I know that as 0 on the decibels, this is 0 decibels, right? we can't hear anything that's less than 10 to the minus. So not that that doesn't exist, not that nature doesn't have that sound intensity. It's just that we can't hear it. We're not, our biology is not set up to, well, most average people anyway. By the way, I guess you must have heard that there are certain frequencies of sound that younger people hear compared to older people. I'm sure you've heard that before, and you also know that dogs can hear certain sounds that humans can't hear. Yeah, so just want to put that out there. It's not quite the same thing of what we're talking about. That's a frequency thing, but yeah, that's something that you probably are aware. You probably have heard that somewhere before. Okay, let's get back to the question. So remember this now. A 0 on the decibel scale corresponds to 10 to the minus 12 watts per meter squared. So can we somehow put that into that formula, right? And come up with what this teacher's decibel level is. I want you to think about that. Let me come back down and show you what the question is saying. This teacher, right, again, not Mr. Kamak, some other teacher, has that intensity when that teacher is talking. So the question is, what does that correspond to as a decibel level? How can we fit all of that into the decibel formula? What is my B1? What's my B2? What's my I2? What's my I1? Can anybody sort of walk me through what that might? So my B1 you're saying could be my 0. I agree. Okay. What else? Do we know the B2? Or is that what we're trying to figure out? Help me out here, folks. What are we in the formula? What is it that we're trying to figure out? Which of these things that's what we're trying to figure out, the B2. Okay, I accept that, Roma. Good. Do we have the I2 and the I1? Do we have that as well? What's the I2 and what's the I1? Let's think this through, folks. Not just Roma, but everybody else. Do we know the I2? So the I1, you're saying, is the 10 to the minus 12. And the I2 is so I1 is the intensity. Okay, I'm trying to follow what everybody's saying now. So the I1, you're saying, is a 10 to the minus 12. And the I1 is the intensity. So what intensity? You mean the one that they gave us for the teacher? Or Hussein is saying that the I2 is 9 times 10 to the minus 9. It's the number that we got. And I'm going to agree with you. That's exactly right. So what we're going to do is we're going to set that up into the formula, right? Oh, by the way, one more thing. Okay, let me see if everybody got this right here. Let me just go back up and have a look. So the B1 is 0. So that's one of the most important things that came out of all of that. Roma is absolutely right. The B1 is 0, right? The B1 corresponds to 0. So in our formula, our B1 is going to be 0. Our B2 is the thing we're trying to find, is equal to 10 times the log of the I2, which we're given as the teacher's intensity, compared to the I1, which is the intensity related to the threshold of human hearing. Okay? So let's put this together. Here we go. So B2, essentially minus 0, which means I'm not subtracting anything, is equal to 10 times the log of this intensity, which is 9 times 10 to the minus 9, over the intensity associated with the threshold of human hearing, which is 10 to the minus 12. Whatever the log of this is, times 10 is equal to B2 minus 0. Why is B1 0? Ryan is asking. Okay, let's look back. And Ryan, it's a good question, and thanks for asking it. And again, I encourage you all, if there's something that's not quite clicking, then you really like Ryan, and congratulate Ryan for doing this, then you really need to stop me and ask, why is this so? Let's go back and look at the formula again, Ryan, and for everybody else. The B2 and the B1 are 2 decibel levels. Okay? That's what B2 and B1 refer to. The I2 and I1 refer to intensities, right? Various rated intensities. And that's measured in real world on its power over a certain area. So it's watts per meter squared. So the B2 is related to the I2. The B1 is related to the I1. So one is a decibel rating and one is an intensity. The number on top represents the louder sound, which is the B2. The number on the bottom represents the softer sound, which is the B1. Now remember, the threshold of human hearing is 10 to the minus 12 watts per meter squared. On the decibel scale, that's related to 0. So this green line here that I'm pointing to right now, right? That's the intensity in the real world. And we have put it on a scale that we're calling 0 at that intensity. So that intensity of 10 to the minus 12 watts per meter squared is related to a decibel level of 0. You see what I'm saying here, Ryan? Right? The number on top relates to the decibel level of the thing that we're comparing it to, which is the teacher's voice. And that is related to the higher decibel level, which is the B2. Okay, great. Thank you for asking. Let's move on. So here's where we are. We actually have at the point now, and I'm just going to point something out to you. This is just simply B2. All right, that's just B2. And this is 10 times the log of. Now, if you think back to your grade 10, maybe, you know that if you divide two things that have the same base, you simply subtract their exponents. So really what I'm looking at here is 9, let's see if everybody sees what I'm doing here, times 10 to the minus 3. Oh, where did he get that from? Right? I just subtracted the exponents. Right? It's actually not 9,000 Induja. It's times 10 to the minus 3, so it's 0.00. Let me just count the number of zeros now. 1, 2, 3. 0.009 is really what it is. Okay? So it's actually a smaller number, not a bigger number. Okay. So, and by the way, where did I get that 10 to the minus 3 from? I took the 10 to the minus 9 and the 10 to the minus 12, and I subtracted their exponents because I'm dividing those two things. So it means that minus 9 minus minus 12, or minus 9. Oh, hold on. Did I do that wrong? It's plus. You know what? I think I had it right the first time, come to think of it, because it is actually a plus. Oh, sorry. It's Induja. I'm going to take that back because it's actually not minus 3 at all. It's minus 9 plus 12. So I should have actually had 9 times 10 to the positive 3. So I'm going to take it back. I shouldn't have corrected you at all. I was thinking it was minus 3, but it's not. It's actually plus 3. All right, so let's keep going here. So 9 times 10 to the positive 3, which is in fact 9,000. So you're right about that. And 10 times the log of that should be my answer. So Alexander is giving me B2 is 39.5, I think. Yeah, okay. So let me restate that. The top is 10 to the minus 9. The bottom is 10 to the minus 12. So that's actually equal to 10 to the minus 9 minus 12. So really it's minus 9 plus 12. Does that make sense? So it's not 9 minus 12, it's 9 minus negative 12 because you're dividing. Okay, so you subtract. So you right. Okay, so that's actually equal to 10 to the 3. So Sindhuja was right all along. Mr. Kamako was wrong, so I acknowledge that. Okay, so I saw earlier on that, was it Alexander? Yes, we're saying it was 39.5. And again, that's decibels. Okay, I'm going to erase all of this here. All right, so this teacher's voice, let's see where this teacher's voice rates on the scale. So this teacher is somewhere between a whisper and a normal conversation, because a whisper is 30, normal conversation is 60. It's somewhere in between those two is where that teacher is. That's a soft-spoken teacher, all right? Not quite whispering, but not quite at the level of a normal conversation at that decibel level. Okay? All right, do we need to write statements to express the answers if the question on test? Absolutely. No, you're right. And I was about to do that. Roma's computer froze. Oh, okay. All right, thanks. Hopefully she's restarting. Believe me, I'm very familiar with computers freezing. I'm quite pleasantly surprised it hasn't done that today. So resetting it seems to have really helped out. All right, so here's my statement. The teacher's voice is rated at 39.5 decibels. Okay, which means I should have put a statement for this one as well. So since I meant to do that, I'll do that now. The sound level, the decibel. So the what is that now? The snowmobile is rated at 100.1 dB. Okay. All right. So are we good so far? Has Roma managed to? Has Roma managed to join us back? Roma, are you still having some issues there? Do you mind scrolling down? Sure, we can. Sure, we can. This will all be in the video. I'm assuming that the video will work a lot better this time. I'm hoping that I'll get my sound and everything, and all will be well in technology land. We'll see. Okay. One more thing we have to consider, and that's earthquake intensities. All right. I'm going to move on to the next slide now. Donna, are we good? You said thank you, so I think we're good. So the third thing that we measure on something called the Richter scale. And, we get earthquake readings all the time. There are earthquakes that happen fairly regularly. In fact, many times we don't even realize that we're experiencing what we call low level intensity. So, again, just like the human hearing can only detect down to 10 to the minus 12 watts per meter squared, we can have earthquakes that we really honestly don't even perceive. We're not aware of. So you can have a zero on the Richter scale. So it's the same kind of thing, very similar to the decibel level, except they don't have that 10. Deci, of course, represents 10, or a tenth anyway. So the only difference on a Richter scale is that we don't have a 10 in it. So it looks very, very, very similar. So the Richter scale reading, and this is not quite the way the book sets it out, but it's the way that I like to teach it. I usually use a very similar formula. Since you've already seen the formula for decibels, okay, so I'm going to suggest that we use a similar approach when we're dealing with the earthquakes, right? Not quite the way the book does it, but this is how I think it's easier to understand. It's a very similar formula. So I use M2 minus N1. So I'm comparing two earthquake intensities, right? And I'm using the I2 over I1 again. I'm comparing their actual intensities. So again, the actual intensities are not the same as the scale that we use. This Richter scale is a log scale. I'm just going to throw something out to you before I even get to the first question. If I told you that, in fact, I'll have an example coming up of the Haiti earthquake. And unfortunately, Haiti experienced an earthquake in 2010, so within your lifetime, in 2010, which really devastated the country. I don't know if anybody has any Haitian connections in the class, but in 2010, they had a pretty bad earthquake, and I don't think they've even fully recovered from that, although that was 11 years ago. At any rate, if I asked you to compare the Haiti earthquake, which was a 7, right, to an earthquake that was let's say a 9. I'm just going to make up a number for now. We're going to do an actual question in a minute. How much more intense do you think one is compared to the other? Right? Just let me just throw that out to the class. It is a log scale. Right? Let me just tell you that it's a log scale. So if one is a 7 and one is a 9, the one that's a 9, how much more fierce, how much more intense, how much more power do you think that particular earthquake has in terms of its intensity? What would you guess if it was a 7 compared to a 9? Let me just throw that to the class and see what you think. Anybody? So you think it's about 3 times more, from a 7 to a 9? Okay, that's interesting. Anybody have another answer that they're thinking? I'm not going to say you're right or wrong. I'm just trying to get a feel for the class here. So a 7 compared to a 9, you think is 3 times more intense. What do other people think? All right, I'm just curious. 7 compared to a 9. We've had 9s, right? We have had 9s, just so that we're actually clear on that. We've had even bigger than 9. Okay? Actually, it doesn't make sense. Okay, all right, fair enough. We're going to make it make sense. Your mic keeps cutting out. I don't know why that is. I'm plugged in. I'm not even using a wireless mic. Thought it was just me. Oh, is my internet off? No. All right. Can you hear me now? Can you hear me now? Okay. Brandon says yes. Yes. I was just looking at my Wi-Fi node here, and it doesn't seem like it is misbehaving. So I'm hoping everybody is okay with that. Okay. Let me restate the question. The question was, Haiti, unfortunately, did have an earthquake in 2010. So again, in your lifetime, that was a 7, devastated the country. And Brendan is now saying things 100 times more intense. Interesting. So one person thought 3, one person thought 100. What do other people think? Right? A 7 compared to a 9. Right? What do you think? Brendan thinks that it's 100 times more intense. What do you think, folks? Are you going to agree with Brendan and think that he's right? Or does anybody have another opinion? Compare a 7 to a 9. Do you think? So Lynette says sure. It's like, whatever. We'll just go with Brendan. Well, let me just ask, is there anybody has a different opinion though? A 7 compared to a 9. Is it really 100 times more just because of that difference of 2? What do you think, folks? Are we just going to agree with Brendan? I'm asking. I'd like to get some more feedback on that. Or a 7 compared to, let's say, a 10. Okay, I'm not sure where Brendan got 100 from. We'll see in a second. But what if it was a 7 compared to a 10 or a 7 compared to 11? What about us? Okay, let's say it's a 7 compared to a 10. Brendan, let's don't give me your answer. Let's see what other people think, right? Just so we can see whether your answer makes sense to other people. What if it's a 7 compared to a 10, right? How much more intense is a 10 compared to a 7? Go on, folks. I'm looking for some answers here. Think about it. If it's a log scale, right? And you see the formula that's there right now. It is a base 10 log that we're using, that they use for that measurement. So what do you think? A 7 compared to a 10. When I compared a 7 to a 9, Brendan said it's 100 times more. What about a 7 compared to a 10? What do you think? 7 compared to a 10. Okay, so Jenna and so are you all agreeing with the original answer that Brendan gave? And Roma is now saying it's 1,000 times more. Is that even possible? 1,000 times more? So I'm going to actually agree with Brendan and also Roma. They're both right. They're both 100% right. Right? That's how a log scale works. So when you compare two things on a log scale, the difference between them is actually an exponent on 10. Oh, well, if they're using a base 10 log, and most times we use a base 10 log. So that's how you need to think about this, right? Whatever that difference is between two earthquakes, put that on a 10, raise 10 to that number because that's an exponent, and that tells you how much more intense one is compared to the other. So Roma is 100% right. A 7 compared to a 10, because the difference is 3, it's 10 to the power of 3, which is 1,000. A 7 compared to a 9, I'm going to say that is 100 times more intense because the difference between a 7 and 9 is 2. 10 to the power of 2 is 100. So you're absolutely right. Okay, let's get to the questions that we actually have to answer, and then we'll probably take our break after that. First question, how many times as intense as a standard earthquake is a 0. Standard earthquake is what we experience every day that we don't actually even know that we're having. The ground is shifting around under our feet all the time, but it is imperceptible. We don't even know that it's happening, right? So we consider that to be a 0 on the Richter scale. So how many times as intense as a standard earthquake is an earthquake measuring 2.4 on the Richter scale? So here's how I'm going to set this up for you. I'm using the M2 minus M1 method that we talked about before. The actual measurement on the Richter scale is 2.4. So 2.4 minus 0 is equal to the log, right? And we're asking is how much more times as intense? So my I2 over my I1 is what we're trying to compare here, right? So what we're trying to figure out is this I2 over this I1. That's the thing that we're trying to find. Okay, hopefully everybody's good with that so far. And that's supposed to be a 1 right here. So this 2.4 minus 0. So this I1 at the bottom is really your standard earthquake intensity. The I2 on top is the more intense one, right? The one that, and that's the one we're trying to find. How many times more intense is one compared to the other is equal to 2.4 minus 0. So what do you think we need to do next here then, right? We're trying to solve for the I2 over I1. What's the next step here? Right, first of all, 2.4 minus 0 is just 2.4 is equal to the log of the I2 over the I1. Okay? So what do you think, folks? What's the next step in the process? Remember, all right, so we're trying to solve for the I2 over I1. So yes, you're right. Thank you, Brendan. So the I2 over I1, maybe you'll see this in about 10 seconds, is equal to 10 to the 2.4, right? And yes, I have written something on the screen. Give it a couple of seconds and it will eventually show up. I have no idea why that is happening, okay? So we're going to actually solve for the I2 over I1. How many times as intense? How many times more intense? So here's what I needed to do, please. As you can see on the screen, I need to find out what 10 to the power of 2.4 is, because that will answer the question of how much more intense that is compared to the low-level earthquake. All right, so can you please tell me what 2 to the 10 to the 2.4 is, please? I need somebody to help me out with that. 10 to the 2.4. That's what's on the screen, 251.2. Okay, great. So I2 over I1 is equal to 251.2. So I'm going to write, it will come up eventually. I'm going to write, it is 251.2 times more intense. Okay? And I think most of you figured out that that was going to be 3 on the Richter scale. And we'll sort of walk you through very quickly why that is. I'm just going to grab a different stylus for this laptop here. Right? So remember that when you compare the two intensities, right, M1 minus or M2 minus M1, so M2 is the thing that we're trying to figure out. M1 is what we're going to be calling 0, is equal to the log of 1 that's 1,000 times more. So it's really like saying 1,000 over 1. So M2 just simply works out to be the log of 1,000. And we already know that in the base 10 world, log of 1,000 is 3. And that's why the answer is in fact 3. Okay? All right. So let's just move on. Let's just try to get this done as quickly as we can. The last question on this is the earthquake in Haiti that I talked about January of 2010. All right. And that had a 7 on the Richter scale. If an earthquake in Costa Rica in September 2 years later was 4 times more intense, what was the reading on the Richter scale to the nearest 10th? Can I go for 2 seconds, please? Okay, there you go. All right, Sindhuja, would we have to show more steps or no? No, there are no more steps on that, really. I mean, the only other thing I should be putting is that a statement. So the earthquake would measure, I'll just use quake, would measure 3. It would be a 3 on the Richter scale. Okay? And my writing on this screen is not going to be, it's already bad on the regular stylus. It's going to be worse on this one. All right, let's go. Let's keep going. One more question left. Yeah, okay, you're welcome. Okay, Natasha. Okay, earthquake in Haiti, 2010, January, was a 7. I mentioned that before. Costa Rica had one in September of 2012, so 2.5 years later, which was 4 times more intense. What was its reading on the Richter scale to the nearest 10th? Let's just follow what we've always done, which is I'm going to put the more intense one first. So we're going to put that as being my M2. I'm going to minus from that the 7, right? Because 7 represents the less intense one. And that's equal to the log of the ratio of intensities. And there's a 4-to-1 ratio on that, 4 over 1 if you like. Give me a second here, make it a little bit better. So that would be 4 over 1, or just simply 4. So really my M2 is just simply equal to the log of 4 plus 7. Okay? So could I ask one of you to work that out for me, please? You're going to be surprised that the number is pretty small. For it to be 4 times more intense, it's not going to be a big difference from a 7. What does that work out? 7.6. All right, thank you very much, Donna. So this earthquake in Costa Rica, I'm giving you actual facts here, in September of 2012 would have been measured as a 7.6 on a Richter scale. But in real terms, it was 4 times more intense. So the Costa Rican earthquake was was measured as 7.6. And you can look that up. Google it. You should be able to find that information somewhere. Was a 6. Or 7.6, sorry, on the scale. All right. Okay, folks, we're going to plot along. It hasn't been the best experience in terms of the technology, but I'm just going to plot along anyway. All right, so hopefully that all made sense. I'm going to go to the second part of the class now. So we've done 3 different log scales. We've done the pH scale, we've done the decibel scale, and we've now done the Richter scale, which measures earthquakes. All right, so one measures the acidity of or alkalinity of a substance, one measures the level of sound, and one measures the earthquake intensities. Those are the 3 things that we tend to measure. Thank you, Donna, and thank you, Hussein, for those answers, by the way. All right.